Alright, so in this lesson we're going to start looking at rotational forces or torques. Now it's probably not surprising to you that there is such a thing as a rotational force. If we've had an angular displacement, an angular acceleration, and an angular velocity, it's probably reasonable to assume that there's an angular force, and there is. It's what's called torque. And what torque does is it causes angular acceleration, much in the way that force causes acceleration. And there are two ways you can cause angular acceleration. One is in the clockwise direction. That's defined as a negative torque. The other one is in the counterclockwise direction. That's defined as a positive torque. Now, the way to determine which direction torque is actually acting on an object is to use what's called the right-hand rule. And there's a description of this here on this little diagram. The way I would describe it is if you have R, the radius of the object, you're going to put the fingers of your right hand in the direction of R, and you're going to put the palm in the direction of your force. What that means is that your fingers will curl in the direction that the object or the angular acceleration will cause the rotation, and your thumb points in the direction of the torque. What that would mean in terms of that direction of that torque is that if this was a screw or a nut or a bolt, that's the direction that screw, nut, or bolt will go. A lot of the same rules that apply to forces also apply to torques. Now, there are actually three variables that determine the size of a torque. One is pretty obvious: the size of the force that's being applied. Larger forces relate to larger torques. The second one may be a little bit less obvious at first glance, but if we think about how angular velocity and tangential velocity and angular acceleration, tangential acceleration related to one another, it then becomes a little bit more obvious. The distance you are away from the axis of rotation. This would be normally what we call the lever arm distance. So how far I'm away from this axis of rotation will also determine the size of my torque. Larger distances relate to larger torques. This angle between force and the lever arm also helps me determine. An angle of 90 degrees would maximize torque. An angle of 0 or 180 would minimize torque. So torque is the largest when F and R are perpendicular, and it's 0 when F and R are parallel or anti-parallel, same direction or opposite direction. Excuse me. So when you think about why that's true, at least in the case of a wrench, longer wrenches generally are easier to use to remove nuts. If you're trying to remove a nut, larger forces are going to be better, and pushing on a wrench perpendicularly will give you the best results. Pushing on either this way down the wrench or pulling out is not going to spin the nut at all. So the equation for torque is F times R times sine of theta. Now there's a little bit more in here. This is technically what we call a vector product in physics. So you have a vector times a vector giving you another vector. We don't need to get into that detail at this point, or at least at this point in what you need to know. What you need to know is that if you take force, radius times the sine of the angle between them, you get the torque. So rank these torques from largest to smallest. And so I'll give you a couple minutes to kind of think about that, and then we'll go through what the results are. The thing that's worth pointing out in all four of these, it's the same beam. So the answer is right here. E and F are the same. The reason why E and F are the same is that in F you have 0 or 180 is the angle between torque and the radius. In E, your radius is 0 because you're trying to push the force where you want it to rotate around. A is the largest, 90 degrees at the largest distance. B is the next largest. Really, this angle is a 60-degree angle. It's close to perpendicular, or it's closer to perpendicular than this is. Between C and D, well, sure, this is more perpendicular, but given the distance here, C is probably bigger. This looks like it's somewhere in the middle of the beam. So that would be your kind of answer for this particular one. Let's do a quick example problem, and this is an example problem from the human body, and the figure on the left shows an ankle joint, and in your ankle joint you have a few different tendons, but the one that is connected to the back of your ankle is what's called your Achilles tendon. It basically connects the calf to the back of your ankle. It allows you to rotate your foot up and down. It's the one that allows you to bend your foot this way, or actually pull your foot that way. So if you're going to run, you need an Achilles tendon in order to be able to run. You actually need it in order to be able to walk too. And let's say the tendon can exert a force of 750 newtons to this point here where it connects. It wants to know to determine the magnitude and direction of the torque of that force about the ankle joint. And it said that the ankle joint is located 3.6 times 10 to the negative second, or 3.6 centimeters, away from that point of connection. It also says that, hey, this thing makes a 55-degree angle with the perpendicular, or that this is a 45-degree angle, if we want to think of it that way. So torque is equal to Fr sine theta. We know F and R. We know theta, 35 degrees, excuse me, I misspoke. Subtracted 100, not 90. That angle's 35 degrees. So if we plug it in, we can calculate the torque, and torque is given in the units of Newton meters. So 15 Newton meters is the torque that the Achilles tendon is putting on the ankle joint, or about the ankle joint. Now, whether or not that's a big joint will depend on what you have on your foot. If it's just a bare foot, this is probably a pretty decent torque. If you have a 15-pound weight on the end of your foot, maybe this isn't that big of a force or big of a torque. We'll start to look at in the next lesson is we'll start to look at equilibrium and what happens if all the torques cancel out. Can I get an equilibrium problem that looks something like the equilibrium problems we dealt with forces?